Well, it's still not a lot of time to go through everything, but I'll try to give you an idea of what's going on in my lab right now. This is a project, this Chemical Rediscovery Survey, something that was started in the beginning of the summer, and it's really based on top of all of the other work that we've done based on open chemistry. So with the time that I have available, I want to deliver those 2 points, that you have some understanding of what we're doing with this Chemical Rediscovery Survey and why openness is so important to it and to accelerating advancement in science, especially in organic chemistry in my case. So first, I just want to go over some of the definitions or some of the implementations of openness, because it means something different to different populations. So, of course, there's open access peer-reviewed publications. So most of you are probably familiar with these, where you can access a journal for free, and generally the author, not always, but generally the author has to pay to have it published. And this is a model that is trying to make science more democratic. But we're still talking about regular papers that it's simply a question of cost. There's been openness in science forever. I mean, informal discussion after a talk at a conference, that is a form of openness. It's between a few people that are in a field, but you're disclosing things that you're not publicly disclosing, that you're not officially disclosing otherwise. Some people think open source software. That's not at all what I'm referring to here, but I'm listing it as something that comes up when people think about openness. Then there's open data sets and models. And here, the word open, when I'm referring to open, I'm referring technically to the CC0 license, which means that you can do absolutely anything with data sets, or, well, let's stick to data sets. So there's no commercial restrictions or anything like that. But if I don't have time to go into details of how you can modify openness. But when I talk about openness, it's basically as far open as you can go. Then there's open notebook science, which is something that we've been doing in my lab since 2005, where the lab notebooks of all of my students are made available pretty close to real time. At least by the end of the day, what they've done in the lab is recorded on a wiki. So I don't want to get into too much of the technical implementations because we don't have time. But the point is that you get to see not only the notebook, but also all of the raw data that was collected by the student, so that someone coming in from the outside has no disadvantage compared to the people working on the project inside. And there's even open research proposals. You can extend this concept of openness many, many different ways. But I thought I would sort of put into context this Chemical Rediscovery Survey in the form of an opportunity here of a paper that came out, Scientific American, a couple of months ago. They were asking, what are the top 5 questions in chemistry? Because the big questions of biology seem to be pretty obvious, right? The Genome Project, but chemistry somehow was slipping under the radar, and someone tried to figure out what are the big questions. And to my surprise, we actually addressed several of these. I think 3 out of 5 of these our project actually addresses, and I'll show you how as I get to that section. Okay. So in order to show you the way that we're doing things, I need to place into context the way that things are traditionally done and how we're doing them differently. So the current paradigm of doing science and of sharing science and chemistry, there's a number of steps. So first, you design experiments based on established or potentially new theories. So what do I mean by that? Is some people build an entire career on developing a new theory. And that will take an entire career to really show that, in fact, it stands up to scrutiny. But if you're not trying to develop a new theory and you're an organic chemist and you're trying to make a molecule, what are you going to do? Well, you're going to design your experiments based on what you find in the literature, obviously. So you're going to be using reactions that have been shown to work. So this is important, as you'll see in a minute, as to how I believe that this is good in some ways, but also has caused some problems. You're going to execute and record the experimental outcomes in private notebooks. So basically, everything that you're going to be doing, unless you have success and you publish it in a peer-reviewed journal, is not going to be shared. So the openness that I'm talking about does not prevent you from publishing in peer-reviewed journals. It's just that everything that is done, including all the stuff that doesn't work or the stuff that ended badly, is also shared. And finally, when a sufficient narrative emerges, selected experimental data are combined to publish with a limited amount of supplementary supporting data. So I have an issue with this, with how much data is actually required from authors, because it can be very difficult to find out how things were actually done. But again, that's a separate issue completely. And we will discuss this at another time. Now, what kind of chemical worldview has this approach created? And this is something that took me quite a while to sort of build up to. Imagine that there are intelligent alien species out there that have organic chemistry classes. What would their textbooks look like? Do you think that they would automatically look like ours? That they would have alkyl condensations, Friedel-Crafts reactions? I'm not so sure. I think that we take a lot for granted about how we build a worldview of chemistry. And the reason for that has to do with selective bias with which experiments are even attempted. So if you can't back up why you're doing a certain reaction in this way, then you don't do it. You don't embarrass yourself. And I'm going to show you why it's actually beneficial to do dumb things, things that you shouldn't do. And I think this is also an issue. Overconfidence in our understanding, since deviant or ambiguous results are rarely reported. So you got to remember, though, that if you're doing a SciFinder search, you're not seeing everything. What you're seeing is what chemists have chosen to report, or were able to report because they're able to form a narrative to form a paper. So you don't know what necessarily was tried and may even have worked or not worked under certain circumstances. So let's see where this takes us. So how can we actually try to fill, I believe that there are blind spots, and I'll demonstrate, I'll have only the time to demonstrate maybe one, possibly two of them. How can you fill in these blind spots? So this is how this Chemical Rediscovery Survey was attempted. So imagine turning the clock back 200 years and just throwing out everything that we think we know about chemistry, mechanisms, even the concept of the solvent, kinetics, all of that, throw it out. And mix things together without prejudice. So obviously, the one thing you want to avoid is things that you know are going to be dangerous if you mix them. But if you remove that component, what happens if you start mixing things completely at random? Well, you randomize the mixture of chemicals with certain criteria, and I'll discuss these in a second, and then simply identify what happens after a convenient period of time. Convenient here generally is 30 minutes and 24 hours. You want to find out if things happen at all, if you reach equilibrium, as one example will show, or if things are changing quickly after 30 minutes and they're continuing to change after 24 hours. These are important things to know. Now, we're not giving up everything. We're not crazy. We're not giving up everything that's been learned in the past 200 years. What we do, though, is we follow up on unexpected behavior with the traditional scientific method. So if we think that we see something unusual, then we pursue that using the hypothesis-driven science, where you say, okay, I think that I'm getting a reduction here because of, and then you design reactions. So it's sort of a 50-50 mix. One, we basically try to randomize things, and then once we find or flag potentially interesting reactions, then we pursue these in the traditional fashion. And the important thing here is that we openly share this entire process, including all the raw data and preliminary hypotheses and discoveries. I'll show you the discoveries that we've made, and they're not what I expected at all in terms of discoveries. Okay, so our criteria, how do we select compounds? Well, because we can do whatever we want, we are going to focus only on small, common, cheap organic compounds. So we are not going to use any inorganics whatsoever. That means no sodium hydroxide even. So can you do chemistry without inorganics? Yes. And I will show you examples of that, although not all of them because we don't have time. But it turns out you can do a lot of chemistry without inorganics. And if we have, since we have the choice of choosing whatever we want, why not select relatively green compounds? So chemicals that are known to be relatively non-toxic, that are known to have a lower environmental impact. This is the future of chemistry in the next 10, 20 years, in my opinion, because there's so many different ways of doing the same thing. And avoid even things that might not be toxic, but that are unpleasant, such as compounds that have stench. So why work in an unpleasant environment? Okay, so how do we do this? Well, we're using something that's actually a lot of chemists might not have heard of. It's called a coaxial NMR tube. So what that permits you to do is to take an NMR of the reaction without mixing it with a deuterated solvent. And that allows you to basically follow the reaction in its native environment. So basically, we have a bunch of these tubes. We have the deuterated solvent on the outside. There's 60 microliters here where you can put your reaction mixture and you can follow it. Like I said, 30 minutes, 24 hours, and you can see what happens. So for example, here, if you mix this compound with this, I would not have expected much to happen. And clearly, most chemists did not expect much to happen because they published the solubility of this compound and similar compounds in alcoholic solvents and didn't report anything unusual. And the reason is they were using GLC, which destroyed one of the fragile intermediates that you see in NMR. So in this case, for example, you'd see a hemiacetal form. So that's kind of interesting because now you've generated a new chemical species. It can't be isolated, but it can be made in situ. And it turns out that last year, someone has published in Green Chemistry a way to turn these into esters and amides under extremely green conditions, just by using hydrogen peroxide. So how do we actually measure this? Well, this is where the open science component really comes in. So what we do is we provide the raw NMR data for analysis. So this is an expansion. We never use paper. There's no reason for using paper anymore for NMR because you can save the file as a JCAM file. And then we have these web services that permit you to view through just a simple web browser and expand by dragging your mouse across any of these peaks. We also have web services that automatically integrate these peaks. So how do we actually get these measurements? These are not done by hand. These are done by using Google spreadsheets that call web services. So again, I don't want to get into the technical issues too much, but if you're interested in that, contact me and I can show you. All of these are free and openly accessible to anyone. But here you can see, for example, the hemiacetal coming in, and that's how we get our ratio. So how do you process this information as you're gathering it? And this is something that we've struggled with. So what we've done is basically create this enormous Google spreadsheet that will have every possible combination of chemicals, right? So we call those an array. And then there's an array transform, which could be just room temperature 30 minutes. And then what happens? So you can either have a stable configuration of molecules that are mixed together. You could have a reactive mixture, or you could have an insolubility event. In the case of an insolubility event, it terminates the reaction because we cannot do NMR on solids. So that basically, so far, most of these have remained liquid. So we basically track the mole fraction over time as these mixtures evolve. And we go even further than that. We assign every single proton on every single one of the chemicals that is actually in the mixture. And this actually turns out to be very interesting because it can be difficult to assign something if you just have one example of it. Once you start to make different analogs of things, it becomes quite obvious which peaks are which. And you can have assistance from NMR prediction software sometimes. It depends on what you're looking at. But for example, here, you can see this basically is the CH3 group. This is the benzylic hydrogen. Okay, you can see it's at 6.07. Now notice something interesting here. It is a singlet. Now, I would have expected it to be a singlet, but it's not always a singlet. So that's actually this fourth discovery here. What kind of discoveries have we been making? Well, a discovery by definition is something that no one's reported before. And we go to great lengths using Reaxys, Scifinder, everything that we have available to see if anyone's ever reported any of these. So to the best of our knowledge, no one has reported what the ratio, what the equilibrium is for 4-chlorobenzaldehyde with excess ethanol. Turns out you get a 10% conversion. With methanol, you get a 20% conversion. And we've observed a very strange thing. Again, like I said, discovery. When I was talking about discovery, I was talking about discovering new reactions. It turns out we're discovering things that don't have anything to do with reactions, but that are very puzzling. For example, we find that in our system, acetone appears at 3.1. And we've repeated this many times. We're trying to understand why that is. But the shifts actually change. If you've ever used acetone or acetone D6, you'll notice it's always around 2.1 or nearabouts. But for some reason, when it's confined into the 60 microliter channel, it always shows up at 3.1. That doesn't change the analysis because we're only interested in the integration. But that is an interesting unanswered question that is a discovery. And if we find a paper that details why that is, we will certainly remove it from the discovery section and move it over to basically linking to the papers that talked about it. And this is the interesting one here, that it's possible for the hemiacetal hydroxyl coupling to be observed even when the alcoholic hydroxyl of the solvent does not. So what I mean by that is what you generally teach in organic chemistry with NMR is if you have ultra pure conditions, you see coupling in ethanol, for example, between the OH and the CH2. And I had always assumed that that's either on or off. It turns out that you don't. You see a singlet for ethanol, but you see doublets with the benzylic hydroxyl groups. So it seems that there's a sensitivity, and that might be exploitable in terms of a sensitivity of impurities, because what's supposed to be causing that is the exchange, does it exchange faster than the NMR timescale? And so this is interesting that not all protons exchange at the same rate. Again, not a discovery that I would have expected. See how we're doing on time here. Okay, I will wrap up shortly. I'll have to skip a couple of slides at the end. But I was showing you this enormous spreadsheet. Now, no human can really interpret that. It's just a whole bunch of numbers. You cannot see patterns in it. And so we've been experimenting with different ways of visualizing this information. And this is one way that seems to work fairly well. What you see here is basically if you mix, these are mole ratios. So initially, right, you've got mainly ethanol with a little bit of 4-chlorobenzaldehyde. The transform here is 25 degrees, 30 minutes. And you see now that you have a new mole fraction relationship. So like I said, you get about 10% conversion. So that's why you see 0.0022, 0.029. And you can see here all of the peaks are assigned. What I want to show you here is, remember I was showing you previously this OH and this H were shown as singlets in the case of methanol. In the case of ethanol, they're actually showing up at doublets, clearly coupling to each other at 7.3 hertz. And if you want to take a look at that, again, the rule is never trust anybody or anything. You can see this is the raw spectrum, and here's the OH, and this is the benzylic hydrogen, clearly doublets. And if I were to show you the ethanol, you would not see a splitting in the case of the ethanol. So that's kind of an interesting result. And I think that it's a different way to think about organic chemistry. You're not just memorizing reaction names and how to make stuff. You're getting into the minds of the chemicals, if you will, in a sense. How do they behave under certain circumstances? So, again, this level of detail for monitoring chemical reaction is not typically available from the chemical literature. So every single reaction that we do on this project is new because no one publishes every single NMR peak. And they certainly don't publish the raw data. How do I know that their starting material is pure? The only way to know is by looking at their NMR, their raw NMR. So, but we still do literature searches to compare, are we getting results that are consistent with what the literature is showing? So, basically the way to think about this is, why do they continuously send more and more telescopes into space? Gaia, for example, is being sent out to look at the Milky Way. Why are we looking at the Milky Way again? Because we can look at it with more detail than we could before, and we're going to discover something. So chemists 200 years ago didn't have NMR. That's why chemistry evolved the way they did. We had UV. We had certain instruments that I believe guided the way that we think about organic chemistry. Now we have a new tool, and it can be used in this way, I believe, to think in novel ways about organic chemistry. So let me see if I can probably skip through most of the rest of these. I mentioned you need a homogeneous solution. Again, if you find something interesting, a new reaction potentially, you can then go back and say, okay, let me go back to my heuristics for kinetics. Every 10 degrees Celsius, I double the reaction rate. So if I wanted to get a 70% yield, what would I have to do theoretically? So you can use the information that you're discovering, and you can translate that into actually doing new reactions if needed. And we have ways of predicting recrystallization solvents. I'm going to skip through this fairly quickly here. So the only one that I really want to focus on from one of the 5 questions is the role of openness and rethinking the big questions. How do we make chemistry environmentally friendly? I think that this is a pretty good approach. If you limit yourself to only using chemicals that are known to be, there's no such thing as a safe chemical, but to limit yourself to using chemicals that are as safe, as cheap, as environmentally friendly as possible, I think you reduce your costs in terms of getting rid of them. I think you discover new reactions. You won't discover a new reaction if you're not looking for it. So that, I think, is where we can make a contribution. Talk about drug design here. How do we tell chemistry to the public? So we're getting about 1,000 queries a day for specific solubility and melting point data. That's a lot of queries. These queries are coming from companies like DuPont, Merck. They're coming from universities, all kinds of universities. People are using these data sets. Now, they're not telling us that they're using them, but we know that they're using them because we know their search terms. So we know that this information is in great demand. I'm going to skip this part here. Going to get to the end real quick. Okay. So we've built models for solubility and melting point, which is not directly related to this project, so I'm kind of going to skip through these. I guess the last thing I really just want to mention that's available, freely available to anyone in the world, and to my knowledge not available from anywhere else, is if you have a Google spreadsheet and you type, for example, benzene or acetone, you can, just by clicking on a drop-down, click on GONS and then click on Get Melting Point, and the melting point will appear. This is an experimental melting point, and there's a link to see where that actually came from. So we have ways, for example, if you want a molecular weight, even if you want a predicted melting point, without leaving the Google spreadsheet, all of that can be done. So you could plan your experiments completely within a Google spreadsheet. So if you want to know more about that, I'll be under ONS Web Services, and that's all the time I really have to talk about that. So in conclusion, I hope I've shown you, I hope that you've gotten at least a gist of why we're interested in pursuing this chemical rediscovery project, and how openness is actually integral to that. If you remove the openness, the project basically doesn't make any sense. And with the openness, you get the information sharing, and you can have people building upon the results that you're finding. So that's it. Thank you for extending the time a little bit.